Namaste students, welcome back to my channel. In our previous video, I end my video with a question that how we can calculate the lambda m naught value for strong electrolyte. In that video, we have studied that how we calculate lambda m naught for strong electrolyte. If you have not seen that video, please go through that video. I'll provide you the link in the description box. So, if we have weak electrolyte and we have to calculate the lambda m naught for weak electrolyte, we can't able to calculate it by graph. So how we can calculate? The answer we will study in this video. The answer of this question is a law which is KOHLRAUSC'S law. So the answer of this question is a law which is KOHLRAUSC'S law. So with the help of the KOHLRAUSC'S law, we can easily find out or we can easily calculate the lambda m naught for weak electrolyte. Now how we can calculate or what KOHLRAUSC'S law is, what KOHLRAUSC'S did, we have to study all these things in this video. Now first of all, if I talk about the history of KOHLRAUSC'S law, means before the development of the KOHLRAUSC'S law, what KOHLRAUSC'S did. So what KOHLRAUSC'S did, KOHLRAUSC'S calculated the lambda m naught for a number of electrolytes, strong electrolytes. What KOHLRAUSC'S did, KOHLRAUSC'S calculated the lambda m naught for a number of pairs of strong electrolyte, and there is a specific feature of those strong electrolyte is that the pairs of strong electrolytes have either the similar cation or the similar anion. Means if I take KCl as one of the electrolyte, then the second electrolyte of this pair is either KBr, in which I have same cation, or I'll take NaCl in which similar anion is there. So KOHLRAUSC'S calculated lambda m naught for a number of pairs of strong electrolyte, and he what is the specific feature of those pairs of electrolyte, that these pairs of electrolytes have similar cation or similar anion. After calculating lambda m naught value for such pair of electrolytes, the KOHLRAUSC'S calculated the difference of the lambda m naught for these pairs of electrolyte. Means first of all, he take pairs of strong electrolytes. In those pairs, the pairs have either similar cation or similar anion. Then for each pair, he calculated the lambda m naught value and lambda m naught value for both the electrolytes of each pair. And then he calculated the difference of the lambda m naught for the pairs. For example, if we take NaCl and KCl, now NaCl and KCl is a pair of electrolyte in which we have similar anion. Then he calculated lambda m naught for NaCl and lambda m naught for KCl through graph, because these are strong electrolyte. And when he calculated the difference of the lambda m naught of NaCl and KCl, then he get that lambda m naught difference is equals to 23.4. Similarly, if we calculated NABR, KBr, means if we calculated NABR and KBr, then also lambda m naught value becomes 23.4. If we take Na2SO4 and K2SO4, then also lambda m naught value becomes 23.4. Similarly, when he take NaCl and NABR, the value becomes 2.06. Sorry, KCl and KBr. When you take KCl and KBr, then the value becomes 2.06. Similarly, when here it is KCl and KBr, when we take NaCl and NABR, then also value becomes 2.06. Then also value is 2.6. When it takes CaCl2, CaBr2, then also value becomes 2.06. What are these values? These are the difference of the molar conductivity of one electrolyte or both the electrolytes. So Kohlrausch observed that if I take the pair of strong electrolyte in which the number of cation, in which the cation, either the cation or the anion is similar, then I get a common difference in the molar conductivity. Then I get the common difference in the molar conductivity. It means the contribution of Na and K towards the total conductivity, the contribution of Na positive and K positive towards the total molar conductivity is definite, and it is irrespective of the fact that whether the anion attached to Na and K is what. Means whether it is Cl, whether it is Br, whether it is SO4, no, means there is no difference. There is no interpretation of there is no role of the anion. Whatever be the anion, the contribution of the cation towards the total molar conductivity remains same. Similarly, here we have anion Cl and Br. Now we are changing cation. So each cation means the Cl and Br have a definite contribution towards the molar conductivity, irrespective of the fact that whether the attached cation is what. Whether it is K, whether it is Na, whether it is Ca2 positive, whether it is Mg2 positive, whatever cation it is, but the contribution of Cl and Br towards the molar conductivity remains same. Towards the molar conductivity remains same. So, with the help of this particular experiment, Kohlrausch's conclusion becomes that each ion make a definite contribution towards the molar conductivity of the electrolyte at infinite dilution, irrespective of the fact that whether the attached anion or the attached cation is what. Means irrespective of the other ions of the electrolyte. So what Kohlrausch concluded, that each ion make a definite contribution towards the total molar conductivity, towards the total molar conductivity of the electrolyte at infinite dilution. We are talking about lambda naught. So lambda m naught is the molar conductivity at infinite dilution, or we can say that limiting molar conductivity. So each ion make a definite contribution towards the limiting molar conductivity, irrespective of the other ion of the electrolyte. Means the contribution of Na is same, irrespective of the fact that whether it is attached with Cl or Br or SO4. Similarly, the contribution of Cl is same, irrespective of the fact that whether it is attached with K or Na or Ca. So whatever be the other ion, irrespective of that particular fact, the other ion has a definite contribution towards the molar conductivity at infinite dilution. And according to Kohlrausch's law, we will write the statement of the Kohlrausch's law now. This is the statement: the limiting molar conductivity of an electrolyte, means whatever electrolyte, the limiting molar conductivity of an electrolyte is the sum of the limiting ionic conductivities of the cation and the anion, each multiplied with the number of ions present in the electrolyte. Means the lambda m naught for an electrolyte is equal to the sum of lambda m naught for cation and lambda m naught for cation, each multiplied with, means each cation and anion multiplied with the number of the cations and anions present in the one formula unit of the electrolyte. Now suppose if I have a formula AXBY, if I have an electrolyte whose formula is AXBY. So for this, if I calculate lambda m naught, for this, it becomes lambda naught for A positive. Here it gets converted into A positive and B negative. So in the formula we have X number of A. So it becomes X into lambda m naught for A positive and Y multiplied by lambda m naught for B negative. So the limiting molar conductivity, this one is the limiting molar conductivity of this electrolyte, is the sum of limiting ionic conductivity of the cation and the anion, each multiplied with the number of the ions present in the electrolyte. Now suppose if I have NaCl as an electrolyte, so lambda m naught for NaCl is equals to lambda naught for Na positive plus lambda naught for Cl negative. Similarly, if I have AlCl3, suppose if I have AlCl3 as an electrolyte, so lambda m naught for this becomes lambda m naught for Al3 positive plus 3 into lambda naught for Cl negative. So here 3 is not the charge of the anion, 3 is the number of the anion which is present in the one formula unit of the electrolyte. Whether I take 2 ACl3 here, still it is the same because I am talking about the one formula unit of the electrolyte. Here we can write that in the one formula unit of electrolyte. So this is the KOHLRAUSCH'S law, and this KOHLRAUSCH'S law is in terms of the molar conductivity. Now if we have to explain the KOHLRAUSCH'S law in terms of molar conductivity, then how we can explain this? You got it? Clear? So this is the explanation of KOHLRAUSCH'S law on the basis of molar conductivity. Now we'll explain KOHLRAUSCH'S law on the basis of the equivalent conductivity. Now on the basis of the equivalent conductivity, if I have to write, so lambda equivalent means lambda naught equivalent for any electrolyte is equals to 1 upon n positive lambda naught for cation plus 1 upon n negative lambda naught for Ni. Here n positive and n negative. What is n positive and n negative? N positive and n negative are the charge present in cation and anion. Is the charge present in cation and anion. In molar conductivity, what we have studied in molar conductivity, it is equals to X lambda positive plus Y lambda negative, and this X and Y is the number of ions present in the electrolyte. This is the difference, present in the electrolyte, and N positive and N negative charge present in the cation and anion. So because of these two difference, we can correlate these two with the help of a formula, and that formula is lambda naught equivalent is equals to lambda m naught divided by lambda naught equivalent equals to lambda naught m or lambda m naught divided by total charge on cation or anion. Total charge on cation or anion. So with the help of this we can correlate these two. So this is 1 upon n naught lambda for cation plus 1 upon n negative lambda anion, where n positive and n negative are the charge which are present in the cation and anion. So if I take an example to calculate lambda equivalent, then how you can calculate lambda equivalent? So it is, suppose I have AlCl3. So when AlCl3 dissociate, what it gives? Al3 positive plus 3Cl negative. So the charge on aluminium is 3 and the charge on chlorine is 1. So lambda naught equivalent for AlCl3 is 1 upon 3 lambda naught for Al3 positive plus lambda naught for Cl negative. Clear? So in this way we can define KOHLRAUSCH'S law either on the basis of the molar conductivity or on the basis of the equivalent conductivity. So we have two different statements for KOHLRAUSCH'S law. The first very statement is each ion make a definite contribution towards the limiting molar conductivity of an electrolyte irrespective of the other ion of the electrolyte. And the second statement is that the limiting molar conductivity of an electrolyte is the sum of the limiting ionic conductivity of the cation and the anion, each multiplied with the number of ions present in the one formula unit of the electrolyte. And in terms of equivalent conductivity, it is means we'll take the sum, but each ionic conductivity of cation and anion is divided by the charge of that particular cation and anion. Means if I have to write down the statement, the limiting equivalent conductivity of an electrolyte is the sum of the limiting ionic conductivity of the cation and the anion, each divided with the charge present on the cation and the anion of one formula unit of the electrolyte. So with the help of this, we can write the statement for equivalent conductivity. Now we'll study the application of the KOHLRAUSC'S law, and in the application of the KOHLRAUSC'S law, we get to know that how we can use KOHLRAUSC'S law for calculating the lambda m naught for weak electrolyte. We'll study the application of KOHLRAUSC'S law. What we'll study? We'll study the application. Its application. Now, the very first application of the KOHLRAUSC'S law is to calculate lambda m naught for weak electrolyte. To calculate lambda m naught for weak electrolyte. Let us take an example. Suppose I have to calculate lambda m naught for CH3COOH. In our previous video, we have taken this example in the graph. So this is a weak electrolyte. We can't able to calculate lambda m naught through graph. So suppose we have to calculate CH3COOH, lambda m naught for CH3COOH. Now according to KOHLRAUSC'S law, lambda m naught for CH3COOH is equals to ionic conductivity of CH3CO negative plus ionic conductivity of H positive. Means if we have ionic conductivity, limiting ionic conductivity, not ionic conductivity. There is a difference between ionic conductivity and limiting ionic conductivity. Ionic conductivity means conductivity of ion. Limiting ionic conductivity means conductivity of that ion at infinite dilution. Clear? Molar conductivity means conductivity of an electrolyte at any concentration, and limiting molar conductivity means molar conductivity at infinite dilution. So there is a difference between normal and limiting. So limiting conductivity of CH3CO negative and limiting conductivity of H positive, as soon as we can calculate the molar conductivity for limiting molar conductivity for CH3COOH. Now, how we get these two conductivity? Now, let us take three electrolytes. CH3COOK, it is a strong electrolyte. KCl, it is again a strong electrolyte. And HCl, it is again a strong electrolyte. Now, if I talk about this, molar conductivity of this is equals to ionic conductivity of CH3CO negative plus ionic conductivity of K positive. This we can easily get through the graph because this is a strong electrolyte. These all are strong electrolytes. So we can easily get the molar conductivity for this. Similarly, lambda m naught for KCl becomes, this is for CH3COOH, this is for KCl. This is my equation first. Lambda m naught for K positive plus lambda naught for Cl negative. This is my equation second. These are according to KOHLRAUSC'S law only. What KOHLRAUSC'S law said, that the limiting ionic conductivity of an electrolyte is the sum of the limiting ionic conductivity of the cation and the anion, each multiplied with the number of the ions present in one formula unit of the electrolyte. This is the statement. So I am writing according to the KOHLRAUSC'S law statement, and I can easily get this value through the graph. Now, third one for HCl. HCl is also a strong electrolyte, so I can easily get this by positive plus Cl negative. Positive plus Cl negative. Now, suppose if I add the molar conductivity of 1 and 3, means 1 plus 2 minus 3. if I add the molar conductivity of first and second, and then first and third, and then I subtract the molar conductivity with second. Molar conductivity with second. Suppose for this, I'm just supposing, I'm just assuming. It is not that I'm writing the exact value. So suppose its molar conductivity becomes 290, its molar conductivity becomes 300, and its molar conductivity becomes 173. So what I have to do? I have to do 290 plus 173 minus 300. This. Clear? So if I do this, what I get? I get lambda m naught for CS3 COO. It is not H, it is K. CS3 COK plus lambda m naught for HCl minus lambda m naught for KCl. So this is the right hand side, this one is the left hand side. Now I'll write the right hand side. Ionic conductivity of CS3CO negative plus ionic conductivity of K positive plus ionic conductivity of H positive plus ionic conductivity of Cl negative. Now minus these two values. So these two are present in positive value. So after writing minus, these two becomes minus. So minus lambda ionic conductivity of K positive minus ionic conductivity of Cl negative. This I get. Now the first statement of Kohlrausch's law is each ion contribute a definite contribution. Each ion has a definite contribution towards the total molar conductivity of the electrolyte irrespective of the other ion of the electrolyte. It means if I have any salt in which I have K positive, then the contribution of K positive is fixed. Whether it is attached with Cl negative, whether it is attached with Br negative, whether it is attached with any anion, its conductivity is fixed. It means here I have same value. It is lambda ionic conductivity for K positive. This one is also ionic conductivity for K positive, means these two values are same. Exactly same, means if it is 123, it should be 123. If it is 144, it should be 144. It means positive negative. If I have plus 2 minus 2, the answer becomes 0. So positive negative cancel each other. Similarly, positive negative cancel each other. So what I get? I get ionic conductivity of CS3CO negative plus ionic conductivity of H positive. And with the help of this, what we can measure? Lambda m naught for CS3COH. So by adding the molar conductivity of these two and then subtracting the value by this value, we get the molar conductivity of CS3COOH. So by using Kohlrausch's law, by using both the statement of the Kohlrausch's law, we can easily calculate the lambda m naught for weak electrolyte. I hope it is clear to you. Now we'll talk about the second application of Kohlrausch's law. It is not that Kohlrausch's law has only one application. It has a number of applications. But the most important application is that with the help of the Kohlrausch's law, we can easily calculate the lambda m naught for weak electrolyte. Now, if I talk about the second, to calculate the degree of dissociation. The degree of dissociation. To calculate the degree of dissociation. Now, what is degree of dissociation? We can represent the degree of dissociation by alpha. And what is degree of dissociation? Degree of dissociation is the number of the electrolytes which dissociate in their solution out of the total number of the electrolytes. We studied in our previous video that for strong electrolyte, degree of dissociation, that is alpha, is always equals to 1, because all the ions get dissociated, all the electrolyte get dissociated through the ions. But in weak electrolytes, only partial dissociation is there, so alpha is always less than 1. But how much less than 1? We can easily calculate through Kohlrausch's law, because our formula becomes alpha equals to lambda mc divided by lambda m naught. So lambda mc we can calculate with the help of the graph. Clear? At a particular concentration we can calculate lambda mc. The only problem is that we can't able to calculate lambda m naught through the graph. So lambda m naught we can calculate through Kohlrausch's law, and when we get lambda m naught, we easily get the degree of dissociation. Means how much it gets dissociated, 70%, 50%, 30%, 20%, 15%, how much it gets dissociated, we get to know through the Kohlrausch's law. Now, our third application of Kohlrausch's law is to calculate the dissociation constant. To calculate the dissociation constant. Now, because these electrolytes, means the weak electrolytes, are partially dissociated, so when the complete dissociation is done, means 40%, 50%, 70%, so when they will dissociate up to their level, up to their limit, then they'll start to make undissociated molecule from the dissociated one. So basically there exists an equilibrium between the dissociated electrolytes and the undissociated electrolyte. Though the reaction is stopped there, means according to us the reaction is stopped because there is no change in the concentration of the dissociated ions and the concentration of the undissociated electrolyte. But there is a dynamic equilibrium between these two, and there we can calculate the dissociation constant. Suppose I have CH3COH. CH3COH get dissociated into CH3CO negative and H positive, and after certain time it comes in equilibrium. So suppose initially its concentration is C, so these two are 0 because the reaction doesn't start in. Now suppose alpha number of moles get dissociated, so its concentration becomes C1 minus alpha. Initially the number of moles of CH3COH is 1, so its concentration becomes C. C into 1 becomes C. Now suppose alpha number of moles get dissociated, so its concentration becomes C1 minus alpha. Clear? Initially, suppose any compound, any electrolyte has 100 molecules, so the concentration is due to the 100 molecules. But suppose after some time 30 molecules get dissociated. Now how many will left? 100 minus 30. So here I will did the same, 1 minus alpha. Initially I will take 1 mole and then 1 minus alpha. So C is the initial concentration, C 1 minus alpha is the final concentration, and alpha number of moles dissociated from here. So alpha number of moles obtained here, because one molecule give 1 and 1. So alpha molecules give alpha and alpha. So its concentration becomes C alpha and C alpha. Now if I calculate the equilibrium constant, which is known as dissociation constant here. So here it is equals to concentration of product upon concentration of reactant, C alpha multiplied by C alpha divided by C1 minus alpha. If I cut C, so it becomes C alpha square divided by 1 minus alpha. So alpha we will get from second, and through lambda m naught we will get alpha, means from first step, from first application we will get second, from second application we will get the third. We get alpha, and with the help of alpha we can easily calculate the dissociation constant. So this is our third application of the Kohlrausch's law. Now we'll move to our fourth application of the Kohlrausch's law, that is to calculate the solubility of the sparingly soluble salt. What is our fourth application? To calculate the solubility of sparingly soluble salt. To calculate the solubility of sparingly soluble salt. Now, what are sparingly soluble salt? The salts like AgCl and BaSO4, which dissolve to a very less amount in the water, they are known as sparingly soluble salt. Means the salt whose very little amount is soluble in the water, those salts are known as sparingly soluble salt. Now, when they form the saturated solution, means a little amount, we will add a little amount of sparingly soluble salt, the solution becomes saturated. So at that time the concentration of that particular solution is considered as its solubility. What is solubility? Solubility is the maximum amount of the solute which we dissolve in the solvent to make the saturated solution. So we are adding a little bit amount of the sparingly soluble salt, and by adding the little amount the solution becomes saturated. So at that time the concentration of that particular solution becomes the solubility of that particular solution. So we can easily calculate the solubility of that particular salt with the help of the formula lambda m naught is equals to K into 1000 divided by molarity. 1000 divided by molarity. Molarity means concentration, and I am saying that their concentration becomes their solubility. How their concentration becomes solubility? Because by adding a very small amount we get the saturated solution, means we get the solubility. So their concentration is solubility, means molarity is equals to solubility. So the formula becomes lambda m naught equals to K into 1000 upon solubility. So solubility becomes K into 1000 divided by lambda m naught. Lambda m naught we can calculate from the first application. K we can calculate from the Wheatstone bridge, which we have studied in our previous video, that how we can calculate K. So K we can calculate from the Wheatstone bridge principle. Lambda m naught we can calculate through the first application of the Kohlrausch's law, and with the help of these two we can calculate the solubility of the sparingly soluble salt. Through graph it is not possible. Why? Because its concentration per unit volume is very less. The concentration of these sparingly soluble salt per unit volume is very less. That's why we can't able to calculate lambda m naught for these salt graphically. And the fifth application is only we have to study there to calculate the ionic product of water. We know that the ionic product of water is 10 to the power minus 14. So how we get the ionic product with 10 to the power minus 14? With the help of the formula lambda m naught is equals to K into 1000 divided by molarity. So ionic product of water means the concentration of the H positive and OH negative ion, means polarity. K through Wheatstone bridge principle, and lambda m naught through ionic conductivity of H positive plus ionic conductivity of OH negative. So this value we can calculate, we can get to know from Kohlrausch's law and Wheatstone principle, and then we will calculate the ionic product of the water. So these are the 5 applications of the Kohlrausch's law. First one, that to calculate the lambda m naught for weak electrolyte. Second one, to calculate the degree of dissociation. Third one, to calculate the dissociation constant. Fourth one, to calculate the solubility of sparingly soluble salt. And fifth one, to calculate the ionic product of the water. So I hope your question is clear. Now if it is not clear, then rewind the whole video, rewind the whole lecture and go through the lecture again and again, so that your question becomes clear, that how we can calculate lambda m naught for weak electrolyte through Kohlrausch's law, and what is Kohlrausch's law, what are the different applications of the Kohlrausch's law. I'll see you in my next video with the questions related to the Kohlrausch's law, and I hope you will solve those questions along with me.